What's up, chemistry? Here we are just outside the dirt bike shed. About to do some graffiti here. That's supposed to be a P. There we go. That's an equal sign. All right. What we have here is the ideal gas law. It's the ideal gas law. And this gas law applies to this can of paint. There's a lot of thing about this can of paint, a lot of common sense that you just understand. One, if you picked up this can of paint, right, you could feel how heavy it was and say, well, I know there's some paint in there. That's this letter right here. This is the letter N. The letter N stands for moles. I know you would like to have an M for moles, but M was already taken. So the letter N stands for moles, okay? The size of this can, I bet you know which letter that would be. Which letter? PV equals nRT. Which one of these letters is going to be the size of the can? That's right, volume. And what makes this can work? What makes the paint come out when I push this button? PV equals nRT. Which one of these letters do you think? That's right, it's pressure. This can is under pressure, and we can measure that pressure. And the last thing is, what if I took this can and I threw it on the fire? Wouldn't that be a problem? Wouldn't that be a problem? Why would that be a problem? Why would this can explode? Well, you like me, Mr. Perkins, one, it would get super duper hot. And the temperature going way, way up would be a problem, right? So this is the formula for something called the ideal gas law. And it states pressure times the volume in a cylinder that is closed is going to be equal to the number of moles times an adjustment number times the temperature. And the temperature obviously has to be in Kelvin. So this one math equation applies to all gases. It wouldn't matter if we had hydrogen, helium, carbon dioxide, propane, methane, anything. Any gas that's in this can under pressure, we'd be able to calculate the number of moles if we knew the pressure on the can, the side of the can, and the temperature of the can. We can also work it another way. What if we knew the pressure on the can, we knew how many moles of gas were in it, and we knew the temperature? What could we then calculate? Yep, we could calculate how big the can was. All of these numbers work against each other in this equation. There are 5 letters, and the only one I haven't explained to you yet is R. Let's talk about what R is. R is an adjustment number. What we have here is a compression tester. You would take this piece right here and put it into your engine, into the hole the spark plug was in, and then you would try to start your engine. And as this needle goes up, it'll tell you how much pressure the cylinder in your motor can hold. Okay? Now if you look closely at this, you'll see there's not one type of pressure listed, but there's 2. Around the outside, there are our North American units only used in the United States, PSI, pounds per square inch. I take that back. Some other countries may use pounds per square inch. And then on the inside, there's a different set of numbers. And the other set of numbers, it says kPa times 100. That means kilopascals. So here we have pounds per square inch and other numbers for kilopascals. So if this needle went up to 150 here on the top, that would mean 150 psi, or it would mean about 10.200 kilopascals. So we need this number R to adjust for what type of letter P we're using. Does that make sense? I'll show you a math equation. All right, here's the math equation. Pressure times volume equals the number of moles times our adjustment number times the temperature in Kelvin. It's got to be Kelvin. And here's our can of paint. I'm going to tell you that the volume of this can of paint, the volume of that can of paint is probably about 700 milliliters. So that would be 0.7 liters, okay? I don't know how many moles of paint are in there, okay? I know the temperature of this can is about 23 degrees Celsius. And remember, we have to add 273 to Celsius, right? Remember the temperature, C plus 273 equals K. So that's how I got 296, all right? And the pressure on this can is pretty high. I'm going to say that the pressure on this can is what we would call about twice the pressure here at sea level. So we're going to give it 2 atmospheres of pressure, right? Remember, we said if you're just standing at sea level, just the air over your head is 1 atmosphere of pressure, correct? Now we've got number of moles and adjustment number left, okay? Now, I can tell you how many moles of gas can fit in this can at room temperature when the can is this big if it's under 2 atmospheres of pressure. The only number I need to look up now is this number for R. And this number for R depends on the units you're using for pressure. Take a look on your chemistry reference tables. Okay, so I'm online. I'm looking at my chemistry reference tables. And you can see right here, it says gas constant R. Page 1, one of the first things. The gas constant, there are 3 different numbers that you can use for R depending on what types of pressure we're using. If you look right here, if we're using atmospheres, see ATM is right there? If we're measuring our pressure in atmospheres, like a weatherman might do, if we're measuring our pressure in atmospheres, then the number for R is 0.0821. So for R, I'm going to put 0.0821. Okay? Now, I want you to tell me how many moles of gas can fit in this can. Solve for N. Okay? I'm going to solve it now. I'm going to say 0.0821 times 296. That's going to go on the bottom over here, right? Boom. That's going to be equal to N. That's 8th grade math. Let me bust out my calculator. 2 times 0.7 divided by parentheses 0.0821 times 296, close parentheses, equals, there's only 0.057 moles, or 0.058, we should round up, 0.058 moles of gas in that can. Okay? Let's try a different problem. Now, since we're in the dirt bike shed, I'm obviously going to have some brake fluid available. And this little container right here, if it's empty, we can calculate how many moles of air are in here. So I open this up, let the air in. I don't change the pressure at all. I just put the cap on it. Now you can tell me, what is the pressure in here? What is the pressure? I just open it up, put the cap on it. You're right. The pressure in there would be 1 atmosphere. It will be the same as out here, except for, instead of using atmospheres this time, let's try to use another unit that the weatherman uses. Let's measure the pressure in this in what we call millimeters of mercury, okay? And 1 atmosphere is equal to 760 millimeters of mercury. It's just a different unit we use to measure pressure. How would I know this number 760? Well, I'll just look right there. I'll just look right here. And if you see where we measure pressure, standard pressure is 1 if we're using atmospheres. It's 101.3 if we're measuring in kilopascals, like the scale for my dirt bike. It's 760 millimeters of mercury or 760 torrents. So these two are the same. Weathermen use millimeters of mercury all the time. So since we're using millimeters of mercury, 760 times the volume, and the volume of this can is 355 milliliters. So I'm going to put 0.355 liters is equal to N. We're going to find out how many moles of air are in there, times R. R is our adjustment number. Since we're using millimeters of mercury, the number for R would need to be what? Look that up on your tables. What is the number you would use for R if we're using millimeters of mercury? Okay, I hope you got that one right, because you literally just had to look it up on your tables. The gas constant for millimeters of mercury is going to be 62.4. So right here for the letter R, I'm going to put the number 62.4. And remember, that's just an adjustment number to make the answer come out right. And what is the temperature here in Kelvin? Well, it's 23 degrees Celsius. That's room temperature. And we have to add 273 to that to convert it to Kelvin. So it's 296 degrees Kelvin. 296 degrees Kelvin. Now we need to solve for the letter N, the number of moles, and I am going to ask you to do that. How many moles of air are in this 355 milliliter container at 760 millimeters of mercury and 296 degrees Kelvin? All right? I'm going to show you how to work the problem again. You'll take 62.4 times 296. You'll put it on the bottom over here. Make sure it's in parentheses. 62.4 times 296. Boom. Take my calculator here. 760 times 0.355 divided by parentheses. 62.4 times 296, close parentheses, equals only 0.015, if we round it off, 0.015 moles of air are in that container. All right? Now, I'm going to ask you a couple of these questions, and we're just going to change the units. Like, I've used atmospheres, I've used millimeters of mercury. There's another unit we use called kilopascals, right? I could give you in a container and tell you how many moles of gas are in it, and give you the other information, ask you to solve for how big was the container, right? So you can be asked for N, for T, for V, or for P. You're always going to look up R. And all you're doing are inserting numbers into this equation and doing 8th grade math. Let's do one more. All right, here's the last problem. I've got my trusty empty can of brake fluid. I opened the cap here, all right, and I'm at 1 atmosphere of pressure, or 760 millimeters of mercury, or 101.3 kilopascals. Those are all the standard pressure. So I put the cap on it, so that's what the pressure is. All right, we know the volume of this can is 355 milliliters, and we know the temperature is 296 degrees Kelvin, and we know right now that there are 0.015 moles of gas in here. But look what I'm going to do. I'm going to take this can and I'm going to set it in front of my heater. And I'm going to make it hotter. Now the can's not going to get bigger because it's got a cap on it, right? So the volume's not going to change. The temperature is going to change. And when I change the temperature, what is that going to increase on the bottle? What is it going to increase? Making it hotter. I can't change the volume because there's a cap on it. So what is it going to increase? That's right, it's going to increase the pressure, all right? So let's work this problem. I set this in front of the heater, okay? What is the new pressure? If the can is 0.355 liters, I have 0.015 moles of gas in there, okay? And let's solve for the pressure in kilopascals. Kilopascals, we're going to have to look up the number R for kilopascals. Swing it over here. The number for R for kilopascals is 8.314. That's what my R is, 8.314. And I heated this thing up. It was 296 degrees Kelvin, but I heated it up by 14 more degrees, so now it's 310 degrees Kelvin. So what is the new pressure on this closed container? It's 0.355 liters. There are 0.015 moles of gas in there. The adjustment number is 8.314. That way we'll get our answers in kilopascals. And now it is 310 degrees Kelvin.